Alrighty, we finish our discussion of Chapter 6 by continuing Section 6.13, where we discussed stereochemistry of these reactions. And remember the shortcut rule that's introduced in this video, but I brought it forward to the previous video, right? Cis, syn, erythro, or cis, where you change two terms. And so the key thing come test time will be remembering that rule. Of course, identifying things are cis or trans to begin with, knowing erythro or Threo from Chapter 4. But what's new from this chapter is remembering the rule and then knowing for each of the reactions, is it a syn addition or an anti-addition? Okay. And if we take this reaction, the stereochemistry of peroxyacid addition, okay, that is a concerted reaction. Okay? And if it's concerted, where everything happens in one step, everything must have to happen on the same side. And therefore, right, peroxyacid addition is always only ever a syn addition. Okay? So if you're cis to start with, you'll be cis or erythro to finish. Okay? So what's the next thought process? Well, what's the other concerted reaction that we had from Chapter 6? Okay? The Hydroboration-Oxidation. That's also only going to be a syn addition. Okay? Getting ahead of myself here, right? Cis, I already alluded to this, starting with cis-2-pentene, going a syn addition, right? We get the cis epoxides over here. Okay. Same thing, right? If it were trans to start, goes through a syn addition, they must end up being trans, okay? Because that changes too. You go from cis-syn-cis to trans-syn-trans. Totally okay. Okay, because it's a concerted reaction. Okay. Now, always keeping in mind, I alluded to this in the previous video, if the three substituents are the same on each side, you're getting one product, right, a meso compound. Same exact idea for hydroboration-oxidation. Because the addition of the borane is a syn addition, the overall reaction, it's a syn and concerted reaction. But the overall reaction is syn. Therefore, if you were cis to begin with, then you're going to be cis in your products. Okay? So these two were cis, they end up being cis because it's a syn addition. Okay. So to summarize so far, right, we had the addition of hydrogen halides and the acid-catalyzed addition of water. Those go through a carbocation intermediate. So if we go from 0 to 2 asymmetric centers, we get a total of 4 stereoisomers. Okay. Now we've seen a couple of syn additions. Okay. The hydrogenation from the end of video 5, and then the hydroboration-oxidation and the addition of a peroxyacid here. Those go from 0 to 2 stereocenters via syn additions. They only form 2 of the 4 stereoisomers. Okay. The reaction that we have left is using the halogens, okay, cyclic Bromonium or cyclic Chloronium ion intermediates when we add Br2 or Cl2. Now this reaction, you'll notice here, it's only an anti-addition because the bromine, when we consider the mechanism, or the chlorine, has to add to opposite sides of the double bond. Okay. The first one adds to the top in this case to form the cyclic Bromonium, but that's blocking the approach of the second bromine. Okay, so the second bromine has to come in from the bottom. Okay, so our bromines have added to opposite sides of the double bond. Addition of a halogen, Cr2 or, Cr2 chromium, you won't be using that until organic 2. Cl2 or Br2 only ever occurs via an anti-addition. Okay. So this reaction is both stereospecific and stereoselective. So now, if I'm starting with my rule of cis-syn-cis, or cis-syn-erythro, right? That's my golden rule that I remember. Well, this is an anti-addition. So if I was cis to begin with, and I change syn to anti, I also must change erythro to Threo, meaning that if I go cis, anti-Threo, that's an allowed combination because I changed exactly 2 words, and those are the 2 stereoisomers I get, the Threo enantiomers, where the hydrogens are on opposite sides. If it's trans to begin with, trans anti-erythro. is the allowed combination where you change two. So I only get the erythro enantiomers where they're on the same side. Okay. And of course, if they're the same, then you have a meso compound, starting to get a little repetitive there, right? If you have an anti-addition to something that was cis, right, then you get trans. If it's cyclic, we're thinking about this as cis. Okay, it's an anti-addition, so the product must be trans because cis anti-trans is the allowed combination. So this is a really useful table from your textbook, table 6.1. Everything's summarized here. Okay, I wouldn't worry as much about the third column, but know for each reaction what type of addition it is. Okay, if we go from 0 to 1 or 1 to 2, that's easy. We just form a racemic mixture or a pair of diastereomers. The challenging part from this ending of chapter 6 is down here when we go from 0 to 2 asymmetric centers. So you have to know the type of addition, right? Is it syn or is it anti or is it a carbocation? Then know that rule, cis, syn, cis, which here is when the textbook finally chooses to introduce it, right? Would have been panic city if we tried to learn all those reactions in stereochem without that rule. That's how you remember it. Know the reaction, know what type of addition it is, so you know if you're putting syn or anti in the middle, and then you can change two words from this master combination, cis syn erythro or cis syn cis. It change exactly two. So these are okay, but notice here, right, cis anti erythro or cis, that only changed one word, so that's not allowed. If it's cis and anti, it has to be Threo or trans. So we finished chapter 6 with a brief discussion of biochemistry. Remember, in my course, the biochem aspect is never tested. It's just introduced for those of you that are continuing on into biochem, right? Because it's important to have that relationship to other courses. We know from previous chapters that biochem deals with the body, okay? But it's not very common to see electrophiles that we've introduced in this chapter in the human body, because those electrophiles would be super reactive. Right? They'd be toxic to you because they'd react with a lot of stuff. But we have a lot of water nucleophile in our body, right? A lot of water in our body. We've seen water act as a nucleophile. And we see reactions get catalyzed by enzymes, which is super useful because enzyme-catalyzed reactions are totally stereoselective. They only ever make one stereoisomer, the one that you want for the biological function, right? So if we take fumarate and react it with the enzyme fumarase, okay, water nucleophile, it forms malate. Only one stereoisomer, right? Only the S stereoisomer in this case, with that one asymmetric center right there. And that is because how things bond into the active site of an enzyme, right, via intermolecular forces or actual bonds, it restricts the directions from which molecules can approach. Okay, so even if I have a carbocation intermediate here, by making water only approach from the bottom, I only get one stereoisomer, the S, okay? Whereas the R would be made if it came from the top. Right, so stereospecific. I'm not gonna take the other stereoisomer. Notice I'm starting with trans. That reaction goes. If I get the cis, okay, no reaction because it's stereospecific. It's only reacting with one of the stereoisomers to begin with. Right. We can also use that to our advantage. The stereospecificity, say that 5 times fast, of an enzyme-catalyzed reaction allows you to separate enantiomers out. Okay, you can actually use this with something like chromatography to separate out a mixture of two enantiomers. Okay, it'll react with one, but not the other, so then you can separate this out. Really important, right? Those enzymes in biological systems. Okay. So to summarize in chapter 6, I've alluded to this in one of the earlier videos, and I think we touched on it at the end of chapter 5, right? As we're going from A to B, we've learned so far, right, how A reacts, and then it ends up making B. But when you're studying these reactions, you're simultaneously studying the process of synthesis, okay? Where we're going to be headed is you're given a product and you're asked to figure out how to make it. So I'll come back to this slide, right? Here's an example of a whole bunch of different products that can be made just from one alkene. But what you need to be, have on your radar for what's coming in the course is you see this and you have to have an idea of how it could efficiently be made, both knowing the reaction and knowing the precursor. Okay. So you're right now learning A, and what it does goes to B. But keep in the back of your mind, okay, how would I make B? So in a very, very broad summary, we've seen in chapter 6 why alkenes react, the kind of reagents with which they react, their mechanisms, and the products that are formed, which all play into synthesis. A bunch of reactions to keep track of within chapter 6. I hope you've been keeping a list. You'll be asked the mechanisms of all these on the tests in some way, shape, or form. And here's a nice little summary on the last slide from the lecture notes, 131. Okay. Taking this alkene, cyclohexene in this case, and looking at all the different reactions that it can do. This was the first one we learned, right? A hydrogenation reaction. Hydrogen and palladium on carbon gets rid of the alkene. It takes it to an alkane. Then we saw addition of a hydrogen halide. Then we saw an acid-catalyzed addition of water. Addition of halogens in an inert solvent. Okay. Addition of a halogen with a different nucleophile present. The peroxyacid, the ozonolysis. Okay. The acid-catalyzed addition of water, the acid-catalyzed addition of an alcohol in this case to form an ether, and the hydroboration-oxidation. Okay. So a nice little summary of everything that's in there. And make sure you know how to do the arrow pushing mechanisms for all these types of reactions. See the alkene and these reactants, know how to predict the product as well.